Hey everyone, and welcome to The Explainer. Today, we're tackling a massive, kind of hidden physical reality behind the digital magic we use every single day. We constantly hear about artificial intelligence, cloud computing, and digital transformation, right? But what we really don't talk about enough is the sheer physical energy cost required to run this new AI-driven world. The absolute ceiling on the future of AI isn't just about coding or silicon anymore, it's electricity. Okay, let's jump right in. Here's how we're going to break this down today. First, we'll look at the true scale of the AI power shock. Then, we'll explore the three pillars of our energy solution. That's natural gas, solar, and nuclear power. And finally, we'll see how this energy triad is literally reshaping the geographic map of the internet. You know, we always talk about the cloud, like it's this invisible, weightless data just floating up in the sky. But the physical reality is actually much different. It looks a lot more like these futuristic, highly energy-dense server rooms. These hyperscale data centers are essentially massive industrial power plants, but instead of manufacturing physical goods, they produce computation. To really set the stakes here, just listen to what NVIDIA CEO Jensen Huang said. AI is energy, AI is chips, the models, and the applications, and we need more energy. He's pointing directly to the fact that the abundance of artificial intelligence is fundamentally, undeniably limited by the abundance of energy we can actually generate. All right, that brings us to Section 1, the AI power shock. Let's take a look at the mind-blowing scale of the energy demand we're actually facing right now. To really wrap our heads around the scale, we just need to look at a single query. A standard Google search requires roughly 0.3 watt-hours of electricity. But a single OpenAI ChatGPT request, that takes 2.9 watt-hours. That is literally almost 10 times the electricity of a traditional search. Now, multiply that by billions of daily users, and you can see why it's driving such unprecedented strain on our power grids. And believe me, the capital markets are reacting. $7.6 trillion. That is Goldman Sachs' projected cumulative AI infrastructure spend between 2026 and 2031. Trillion with a T. To put that number into perspective for you, we are talking about the largest industrial capital deployment of the modern era. We're basically building the railroads of the 21st century, and those railroads run entirely on massive amounts of electricity. According to data from the Electric Power Research Institute, data centers consume about 4% of United States electricity today. But based on high growth projections driven by AI, that could skyrocket to 17% by 2030. Just think about that for a second. That single sector's power demand would be roughly equivalent to the entire electricity consumption of the country of Japan. So how on earth do we power all this without totally collapsing the grid? Well, that takes us to Section 2, natural gas, our near-term fix. We're facing a really tough engineering reality here. There is this massive friction between how fast AI software scales, which is almost instantly, and how incredibly slowly energy infrastructure scales. Over the next 2 to 5 years, natural gas is absolutely going to dominate because, frankly, it's the only resource we can deploy fast enough. It's going to act as the bridge, while nuclear and large-scale solar require a good 5 to 10 years to truly scale up. Because of current policy environments and the sheer breakneck speed of development, natural gas is currently winning the least cost procurement race, hands down. In fact, projected new build rates for natural gas capacity are expected to more than double their recent average. When these tech giants need rock-solid power for data center opening in just 24 months, natural gas is currently the most viable answer on the table. Let's look at how this plays out in the real world. Meta is currently building a 1.5 gigawatt project down in Louisiana that heavily relies on gas turbines. The demand is so crazy right now that gas turbine orders actually exceed manufacturing capacity all the way out to 2031. Now, relying on gas does introduce some real constraints. It increases exposure to global market price swings, and of course it adds to emissions profiles that many tech companies are actively trying to reduce, which is exactly why they're aggressively looking at alternatives. That brings us to Section 3, solar, the intermittent scaler. To understand solar's role in all this, we got to talk about capacity factor. Simply put, this is the ratio of actual energy produced compared to the maximum possible continuous output. The crucial point here is that solar has a capacity factor of only about 24%, mainly because of cloud cover, weather, and the fact that the sun goes down every night. The problem? AI data centers never sleep. They demand 100% capacity factor, 24/7 power. And this creates an absolutely enormous land use challenge. An average modern data center footprint is relatively small, But a commercial solar field requires about 7 acres of land per megawatt. Say you have a major tech hub with 250 average-sized data centers. To power them purely on solar, factoring in that low 24% capacity factor, it would require a staggering 700,000 acres of solar panels. In some regions, that is literally double the landmass of an entire county. So the big takeaway here is that while solar is a wonderfully clean and essential piece of the puzzle, it is highly intermittent. To make it work for always-on AI, we need massive secondary infrastructure investments, vast tracts of land, entirely new high-voltage grid transmission lines, and gigantic utility-scale battery parks to store power for the night. And because of those hurdles, the tech industry is turning heavily to the final pillar, Section 4, nuclear, the long-term baseload. Look at the direct contrast here. We've got solar, highly intermittent with that 24% capacity factor. And on the flip side, we have nuclear with a near 100% capacity factor, providing 24/7 baseload reliability. Even though nuclear plants take way longer to build, that near 100% capacity factor is exactly why tech giants are drawn to it. It provides the constant, ultra-dense, carbon-free output that AI data centers desperately require. And we're seeing massive global moves on this front. China is taking a highly pragmatic approach, currently building roughly 30 of the 60 nuclear reactors planned globally by 2030 just to stay ahead of their own AI demand. Here in the US, small modular reactors, or SMRs, are expected to be viable in about 5 years. And companies like Microsoft, they're already exploring partnerships with local providers to secure this long-term, carbon-free nuclear capacity to expand their regional grids. Okay, now that we understand the energy triad, gas, solar, and nuclear, let's look at Section 5, reshaping the data map. AI requires totally different infrastructure on the inside of the data center too. We're seeing a massive shift to next-generation high-voltage direct current architectures, which sounds super technical, but it's basically necessary to prevent massive energy loss when you're moving that much power around. Because AI workloads run incredibly hot and demand unbelievably stable power, developers are having to completely rethink how electricity is distributed. And because of these massive power needs, they're being forced to look way beyond your traditional tech hubs. Power availability is actually creating clear winners and losers in the real estate market now. According to a recent report, legacy markets like California, Iowa, Oregon, and Nebraska are projected to see market share declines of over 50% simply because of grid bottlenecks and permitting complexity. Meanwhile, emerging winners like Mississippi, Oklahoma, and the rest of the US are seeing a 21% increase. Power-abundant states are unexpectedly becoming the new AI capitals. And guys, here is the absolute kicker. Even if we completely stopped building brand new data center facilities today, our power demand would still skyrocket. Why? Because the servers inside are changing. Inside a modern AI rack, power density is jumping from 12 kilowatts to up to 120 kilowatts per rack. That is a 10-fold increase in power demand sitting in the exact same square footage. It's placing intense strain on local electric grids. Now, you might be wondering, hey, won't our computer chips just get more energy efficient over time? Well, yes, they will, but we have to remember the Jevons paradox. It's an economic principle that states when technological progress increases efficiency, the rate of consumption actually rises due to increased demand. Making AI chips more efficient won't save power overall. It'll just democratize AI, making it cheaper and more useful. And that leads to massively more usage. As one industry expert put it, at the end of the day, a 200 megawatt data center is always going to consume 200 megawatts. Which leaves us with this one really big final thought. If AI efficiency simply leads to more capability and therefore way more energy consumption, is there a limit to how much physical power we are actually willing to trade for artificial intelligence? The physical world and the digital world are completely intertwined now, and our energy choices over the next decade are going to define the limits of human technological progress. Thanks so much for hanging out with me for this explainer. Keep learning, keep questioning, and I'll catch you next time.